Okay, let us start. So far we have seen that logic is a branch of philosophy as well as mathematics, where we study how to reason, and we would like to know answers to various questions. In mathematics, we want to know what is the difference between structure and properties, what is the difference between polynomials, polynomial equations, solution sets of polynomials, polynomial functions, those kinds of things. What is a theorem? What is a theory? Yeah, how a theory differs, a theory in mathematics differs from theories in other science areas. And in order to start that, I mean, we are going to, in this course, we are going to look at two different types of logics. The first one is called propositional logic, which is the baby version, and then we will study first order logic. So the difference between these two logics is that the propositional logic is logic of connectives. So which means you are going to start with some sentences, you don't question anything about them except for whether they are true or false, and then you construct new sentences out of these existing sentences. So these sentences that you begin with, you will treat them as indestructible atoms. Yeah, I mean atom as in indestructible. So you don't go inside that particular sentence. You just say whether it is true or false. Apart from that, you don't do anything. And in the first order logic, however, we will try to convey the idea of truth in a more meaningful way. There will be some more delicate way of dealing with sentences. You will have some quantifiers embedded inside your language. Right? So connectives means and, or, implies, negation, those kinds of things, simple things. And quantifiers means there exist and for all. So right now we are not talking about quantifiers, we will only talk about propositional logic, which is the logic of connectives. So whenever we start with some new area, be it science or be it mathematics, we always have to know what is its terminology. Right? So first of all, whenever we are starting with a logic, we need to know what is the alphabet. So the alphabet of propositional logic consists of two things: a language and meta language. Language is something variable. Okay, it will change according to our, I mean in this case we will say it's a propositional language. And meta language, on the other hand, it is fixed. It is coming from the meta level. Okay, it is fixed and it consists of something simple. Yeah, so this consists of parenthesis. Yeah, parenthesis we don't want to change according to our wish. Yeah, they are always there. Then conjunction. Conjunction is a binary connective. Binary connective means it connects two different things to give one new thing. And negation. What is the arity of negation as a connective? Unary, one, right? It's unary connective means it just says that this is not true. That's our intended meaning. So let me write here. So binary connective and this one is unary connective. Actually, our language, a meta language, can only consist of these four symbols and we are happy with that. However, in practice, in practice we will also use these symbols, right? disjunction, then implication and by implication. Okay, let me write down some names. So this one is called conjunction. Then negation, then disjunction, implication and by implication. Now you might be wondering that we have seen similar symbols in Boolean algebras. Okay, so what are they called? Conjunction is meet. Yeah, I mean the same symbol represents meet. Then negation, what do we call it? Complement, very good. Disjunction, what do we call it? Join. Implication, yeah, I mean it's called implication and by implication, those are the same names. Now, so far what I have not described is the language. You understand meta language? Why it is called meta? Because we do not want to change. Yeah. So, for now, yeah, for a few classes, these symbols are not going to be important. These two symbols, will call them basic, and these ones will call them derived. Yeah, they are derived from the basic symbols. Can you tell me how disjunction can be derived from conjunction and negation? De Morgan's law, exactly. What is the meaning of implication? Negation A or B. Correct? So that much you know. And what is by implication? Negation B plus. Not plus. There is no plus. A implies B and B implies A. Yeah, we'll see all these things later. But therefore they are derived. And we have used this idea once before, last week. Can you tell me where we only talked about conjunction and negation and nothing else? Homomorphisms. Homomorphisms preserve negation and conjunction, and then we never worried about anything else. Everything else was automatic. Okay, we are not yet done. I should add two more symbols. T or top and bottom for false. Okay, so this one stands for truth and this stands for false. I mean true or false. Yeah, I mean those are the symbols. Because our logic, yeah, we are not trying to say that I am sometimes lazy. If that's a statement, then that has some sense of quantifier. Yeah, sometimes is a quantifier. We do not want to talk about such statements. Our world will be black and white. Something is either true or it is false. There is nothing in between. Right? So that's why only two symbols. I accidentally might write T and F. Yeah, please correct me if I do. Yeah, so truth and false, those are the only two symbols. Okay, now what does the language consist of? So language is simply a set. Yeah, usually countable and most likely finite. Okay, it is just a set. We use letters P, Q, R to denote elements of the language. Yeah, I mean they are called propositional elements of the propositional language. And okay, so the notation that we use is usually L. Yeah, L stands for language. Yeah, no surprise here. Lattice L, poset P, well ordered W, yeah, language L. But it's a curly L. Yeah, we will distinguish it from a lattice. So L is equal to, yeah, I mean generally we write something like this, P1, P2 and dot dot dot. That's our language. So these are just placeholders. So let me give you a quick example. Yeah. My first statement is that the moon is made of pi. Is it sensible? Don't care about it, whether it is sensible or not. Yeah. Mice like cheese. Yeah, this is another statement. And then I am saying it is not the case that the moon is made of pi. So if the moon is made of pi is the statement P, I am saying it is not the case that the moon is made of pi. So what is that statement? Negation P. That's how we are going to work with it. Don't care about what's inside. Just care about how things are connected. Right? So, did you observe something very specific here? I did not say the moon is not made of pi. I did not touch the sentence that was there. I said it is not the case that. So I can say that person X is a good student. Okay? And X is a fixed person. Now, if I want to say its negation, what should it be? It is not the case that person X is a good student. I am not going to immediately change good to bad. Yeah, there are different logics which will deal with that kind of situation. Our logic does not change the internal portions of the sentences. Understood? The moon is made of pi and mice like cheese. This is P and Q. P and, I mean, in our normal language, what does it stand for? And. This is not. Well, let's also mention those things. I will use green color or maybe red color. Yeah. This stands for and. This stands for not. This stands for or. Then this stands for if then. And this stands for if and only if. So there are three different types of languages we are dealing with. One is the language of Boolean algebras, another is the language of logic, meta language of logic, and third one is our usual human understanding. So propositional logic will establish one-to-one correspondence between all of them. Yeah, so in these two lectures we will go there. So you understand what is what these P1, P2 stand for? They are just sentences. And then we are going to talk about whether they are true or false. We won't worry about what those sentences are those meaningful, how they are constructed, nothing. They are indestructible. Understood this part? Okay. So this is our language, and so alphabet, what is English language alphabet? What does it consist of? A, B, C, D up to Z. Then there are some meta language symbols also. Huh? Punctuation marks. Then also space. Without punctuation marks and space, we cannot construct sentences. So similarly, with a language, now we have the alphabet, we should construct sentences. We'll call them formulas, but they are sentences also. This distinction will be clear between formulas and sentences once we study first order logic. So, okay, so let's start with that. The set of sentences or formulas for a language L, for a propositional language L is defined recursively as follows. Okay, I want to make two more comments. That first, whenever we are talking about logic, then your language has to be precise. Yeah, that's one of the most important things to learn about foundations of mathematics. I mean, your language has to be precise doesn't mean this language. I'm saying the way we speak about mathematics, that will become more precise if you study logic properly. Yeah, that's one of the major goals of teaching you logic, that your language becomes polished. Okay, so even like these small propositions, like, see, there are so many common things. Yeah, propositions. For. Yeah, this for a language L. Formulas for language L. Yeah. Now, you cannot say formulas of a language. Everything has to be very precise. Okay. This one I am going to say SL. S is ordinary, L is curly. Recursively as follows. What is the base case? Each propositional variable is an L formula. Okay, each propositional variable is an L formula. We had to start somewhere, and the only place we can start with is whatever is given to us, and then we can form long sentences with them. And then this recursive case. So if S and T are L formulas, this is my way of writing it shortcut, yeah, FMLA formulas, then so are negation S and S mate T. And then there is a third clause, yeah. So this is neither base case nor recursive case, but I mean, if I call this 0, 1 and 2, then the most important case, important clause, it reads, that's it. Okay, what does this mean? That there is nothing else which is a formula. Only the things which we can construct using base case or recursive case, only those things are formulas. Nothing else is a formula. Right? So in every definition we write about formalism, this clause will be present and it will be the most important clause. So here note something, that we are talking about parenthesis negation S. Without parenthesis it won't work. Right? So you have to be careful about it. So let us look at some examples. If L is equal to P, then some L formulas are obviously P, then P conjunction P, then negation P, then P conjunction negation P, then negation of P conjunction P, and dot dot dot. How many such formulas would there be? Infinitely many. Even when you start with a singleton language, yeah, there will be infinitely many propositional formulas. Okay, this is one of your tutorial exercises, that if your language is countable, show that the collection SL is also countable. Always countably infinite, non-empty count. If your language is non-empty, then it's always countably infinite. Okay, so then these some L formulas are like this, and if L is equal to PQ, then what will happen? Some L formulas are, tell me. We'll start with P and Q. Yeah, don't jump to something fancy. Then P, negation P, negation Q, then P conjunction Q. Anything else? Negation of P conjunction P, yeah, and so on. Right, so you can write down infinitely many formulas. Yes, let us go back a bit and let me write that we use letters STU to denote L formulas. Okay. So we are going to use only very specific letters to denote something specific. PQR to denote elements of language, STU to denote formulas. Yeah, this distinction in our mind is very important. Right. So this base case and recursive case, see, this is not our usual type of induction. This is called, recursion or induction, this is called recursion on the complexity of formulas. Yeah, this is not our usual type. And we can also write SL as using our usual recursion. So, alternate definition of SL define S0L equal to L and Sn plus 1L equal to SNL union negation S, comma, for all S in SNL union S conjunction T for all S and T in SNL. And then, so finally, we set SL equal to union of SNL where n is less than omega. So now tell me how, where is P, this particular P? In which SNL? What is the n? 0. This meet P conjunction P? 1. Negation P? This one? 2. Now, can you easily recognize which SNL it belongs to? What do you do? Number of parentheses. Okay, very simple idea. Just the number of parentheses will tell you which SNL it belongs to. Okay. Now, one observation that you might have made so far is that, yeah, so this is observation, but you are supposed to prove it. If L and R, L blank and R blank denote the numbers of left and right parentheses respectively. Then for any S in SL, LS is what? Is equal to RS. How will you prove such a result? How will you prove such a result? If you want to prove anything about SL, SL is recursively constructed. So what is the method of proof? Induction. Oh yeah, I earlier said that there are two things to discuss and I only said one. The second thing is we try to use very minimal set theory while doing this. We only assume existence of finite or at most countable sets. Yeah, we don't want to do anything more complicated than that. So therefore our proof techniques are also going to be limited to, I mean at least in the first part, this formalism part, our proof technique is going to be limited to only induction, because that's all we know. Yeah, even though you have studied more set theory than this, yeah, logic is an independent branch of mathematics, and at the meta level it should not assume too much set theory. That will change as the time progresses, but for now we don't want to use anything more. Now another observation, so we can call this observation 1 and observation 2. See, if I take any formula and I take its initial subword, so for example I can take just this part, or I can take just this part, I can take just this part. So non-empty initial subword of a formula, then the number of left parenthesis and right parenthesis, how are they related in that subword? Exactly, left is more than that, and therefore what can you conclude? That no proper left subword, non-empty proper left subword can be a propositional formula itself. Yes, it's an observation, but again you are supposed to prove it. If W is a non-empty proper left subword of S in SL, then L of W is bigger than R of W, and hence W does not belong to SL. Right, so a formula is a whole on its own. Yeah, you cannot break it into two parts. Two things cannot be formulas. And for this reason, these parentheses are really crucial, because everything is really based on around parentheses, just counting of parentheses. In practice, tell me, do we write so many parentheses? It's cumbersome, right? And also, if I just want to say that P implies Q, how complicated would it be? What is P implies Q? Yeah, I mean this is just an aside, I will write it here. So P implies Q is a shortcut for negation P or Q. But negation P or Q, we don't even have or, right? Disjunction we don't have. So it is negation negation P and negation Q, and then this. Well, we don't want to write this. Huh? Oh, what happened? Have I not written it correctly? I missed parenthesis 1, 2, 3. 2, okay, here. Thank you. There should be one more, right? Okay. See, this is the mess we create if we write all the parentheses. Now, if we just want to say something like P implies Q and we are making so much mess, we don't want that. So, first, based on these two observations, we will state a theorem which is easy to prove from these two observations, and then we will try to add some derived symbols in our language. Okay, so let us go to the next page and say that. So, this looks boring, but it is extremely important. Unique readability theorem. If L is a propositional language, and S belongs to SL, then S is exactly one of the following forms. First one, S belongs to L. Second one, S is equal to negation T for some T in SL. And third one, S is equal to T conjunction U for some T and U in SL. Okay, you might think I have just written down the definition again, but that's not the case. In the definition, I said that you start with propositional variables and then you use two rules, either negation or conjunction, to construct new formulas. But I am saying that if you like any formula can be constructed in exactly one of these two ways, or it itself is a propositional variable. There cannot be anything else. You understand? That a formula which is negation of something cannot be a conjunction of something. Right? It cannot happen suddenly that negation T is same as T1 conjunction T2. And how do you prove something like this? This is just manipulation of symbols, there is nothing else. How do you prove something like this? Using those two observations. Because if something is of the form, I am giving you a hint, if something is of the form 2, then the first symbol must be parenthesis, the second symbol must be negation. Even if T itself is a negation, in the third form, even if T itself is a negation, there will be a parenthesis before negation. That's how we constructed it. Right? So therefore, there cannot be two different construction trees for the same formula. Construction tree is a term used for this. So if I want to construct this, if I start with P and negation P and Q and then negation, then how do I start? Well, first of all, it is a negation. So I should write this. Here in the tree I am applying negation. Then this is conjunction, so it is coming from two different things. First one is negation P and the second one is Q, and this is the conjunction part, and this is P and this is the negation part. So basically, unique readability theorem says that every single formula has a unique construction tree. Why is this important? All of you know some level of programming, yes, coding. In coding, if you write if you have one wrong symbol, then your program does not run. So therefore, every symbol should be in its proper place. So there is unique readability to the codes that you write. So that is what this says. Okay, you cannot write something with ambiguous meaning. Okay, so again, this is easy to prove using those two observations. Okay, at this step, this is the right place to use derived connectives. We use disjunction, implication, and this. Okay, how do we define disjunction? We already know. So S disjunction T is same as negation of negation S, conjunction negation T, and this. Then implication is negation S, disjunction T, right? And by implication is implication, conjunction, another implication. So these are in increasing levels of complexity. Then we do not use so many parentheses in practice. So, but we use some conventions. Okay, what are the conventions? So, negation binds closer than all of the other symbols. So, for example, if I write negation P and Q, then what does this mean? It means negation P first and then conjunction Q. It doesn't read as negation of P conjunction Q. If I want to say that, then I should put parenthesis. So the rule is that negation binds closer than any other symbol. Similarly, so conjunction and disjunction, they bind closer than implication and by implication. Yeah? These are the common things which we use. Yeah? Whenever you read a formula, then you read them using these things. So that now we don't have to use so many parentheses. Yeah? Our life will be easy again. Any questions so far? No? Okay. So, yeah, I mean just, well, perhaps I should give you a non-example of a formula. If I just write this, is this a formula? Yeah, it's not obtained from anything, then so is not. Yeah, these look nonsense. And that's the purpose of this last clause, yeah, that's it, that we do not allow anything else. So you understand the formalism? We have our alphabet, which consists of language and meta-language, and using that alphabet, we construct what are valid formulas. Oh yes, I did not say this, I should add. Yeah, some people will call them well-formed formulas, especially if you read some books and abbreviated as WFF. However, I am not calling them well-formed formula because I never understood when did we define ill-formed formulas. We never define them, so therefore all the formulas we talk about are well-formed. So I am not going to use that terminology. Okay. Let me go to the second slide. Now look at these things. P conjunction P, then I can also add P conjunction P, and so on. So even with something as simple as P, we have infinitely many formulas. And most of them look the same. Yeah, to us, to our eyes, they look the same. P conjunction P. What will be the shortcut to write that? P. Then P disjunction P. Also, if we write, it should be P. But a computer doesn't understand that. For a computer, everything is a string of symbols. We have to write all of them. However, here enters human semantics. Because we understand that P conjunction P should be P, we have to make sure our understanding is exactly the same way. So let me start with the semantics part of our propositional logic. So PL semantics. So what is semantics for us? It is called a valuation or a model, because there is a branch of logic which is called model theory. Nothing to do with fashion industry. Okay, model is, so in simple sense, a group is a model of the theory of groups. A ring is a model of the theory of rings. So the theory of rings will come first, and then a ring is a model of that theory. So in the same sense, now this is a baby example. So let me write that down. For a propositional language L, a valuation or a model for L is a map. Map means function. V from SL to the two element set, truth and false, satisfying the following. Okay, so first one, V of negation T is equal to true if and only if V of T is equal to false for all. Oh sorry, please add it here, for all T and U in SL. Then I can erase this part. And then second condition, V of T conjunction U is equal to T if and only if V of t is true and V of u is true. Okay, let me add one more if and only if here for the first clause. If and only if V of t is not equal to true. So, if you have copied this down, let me quickly go back to the first slide. See, there was something red. Red stands for and not, and the black stands for conjunction and negation. Now, this definition is trying to give a connection between those two. Read this. V of negation t is true if and only if V of t is not true. You can see the transformation. Yeah, this not is our understanding. Similarly, in the second clause, V of t conjunction u, so this is conjunction, is equal to true if and only if V of t is equal to t true and V of u is equal to true. So, we are converting these symbols into our usual meaning. Yeah, that's how the definition goes. Okay, so can you tell me, where should we start in order to define such a valuation? It's an arbitrary map which satisfies these two values. Okay, so let me give you an example. So, let's first do that. If L is equal to PQ, then V of P is equal to true and V of Q is equal to false. Then V of P conjunction Q is what? Tell me. False. Because this property is not satisfied, the second one. V of t is equal to true, but V of u is not equal to true. So, therefore, we cannot say that the conjunction has this. Normally, what do we do for such things? You already have some truth tables, very good. So, now here is where the truth tables enter, right. So, simple thing, let us do this. So, we have truth tables. So, we have P, we have Q, then suppose we want negation P, then we want negation Q, then we want P conjunction Q, P disjunction Q, P implies Q. Right. So, and maybe I will slip in one more thing over here, negation Q, P by implication Q. If both of them are true, what will be negation P? False. Negation Q? P if and only if Q by implication true. P and Q, P or Q, disjunction, and P implies Q. Okay, how many entries should I fill up for P and Q? 4 entries, yes. So, there will be 4 rows, and in general if I have n variables, then 2 to the power n, yeah, not 2n, 2 to the power n. So, let me fill this up. So, true and false, yeah. So, negation P is still false, this is true, then, well, let me first finish this, false and true and false and false. Negation P will be exactly the opposite thing, negation Q will be this. P if and only if Q is true, if and only if valuation of P is equal to valuation of Q. So, true true will give me true, true false will give me false, false true will give me false, and true false false will give me true. False false will give me false, true, because they are equal. Yeah, that just checks whether they are equal. Then P conjunction Q is true if and only if both of them are true. So the rest of them I should write as false, false, false. And disjunction is true if and only if one of them is true. Yeah, or our meaning of or, either P is true or Q is true. So I should say true, true, true and false. And P implication Q is true if and only if either our premises are wrong or our conclusion is true. So therefore it only becomes false in this case. Yeah, let me quickly write that down, that V of S implies T is equal to true if and only if, I shouldn't write if and only if, I am always going to be careful, if and only if V of S is false or V of T is true. All of you know how to draw truth tables, right? Nothing hard about that. So tomorrow we will continue our discussion about semantics, and then we will see the notion of logical equivalence between formulas, so that P conjunction P becomes logically equivalent to P, and then we can treat them as the same thing. And these logical equivalence classes, there is a word equivalence in there. So the logical equivalence classes will form a Boolean algebra, whose meet and join and complement, they will coincide with our usual logic operations.